In this video, we're going to look at modeling with trigonometric functions. In particular, we're going to look at sinusoidal functions. We're going to model equations using graphs of sinusoidal functions. We're going to model periodic behavior. We're going to model harmonic motion functions. Let's take a look at our first example here. We have this Ferris wheel that has a diameter of 60 meters and rotates once every 4 minutes. So first of all, this tells us that our period is equal to 4. So right out of the gate, we already know what omega is if we were asked to write this as a sinusoidal function. The center of axes is 40 meters above ground. So here's where my axis is right here. So this is kind of like where our midline has moved to. If we were to get a passenger on this Ferris wheel, they would start obviously when the Ferris wheel is at the bottom. So they would start right down here, right here. So they'd start down here. And of course that would relate to here. And the reason that relates to here is because the entire diameter is 60. That means the radius must be 30. So that means the platform must be 10. Now, we know that the person who gets on this Ferris wheel after 4 minutes will be back down at the bottom, right there. So we also know halfway, they should be the 30 plus another 30. So we have to have a diameter there. So we have the 10 plus the 30, which tells me at the 2-minute mark, they're 70 minutes or 70 meters up. Now, if that's 30, that means this is 30. So we know what the amplitude would be. And the graph at the quarter mark, right? At the quarter mark, they'd be here and here, the quarter and 3/4 mark. And at the halfway mark, they'd be at the very top of the Ferris wheel. So again, here's the bottom that represents this. Quarter way through the ride, they're right here. Halfway through the ride, they're at the very top. 3/4 of the way through the ride, they're right here. And then, of course, at the end of 4 minutes, they are down here again. So we can see that this is clearly a cosine wave because I'm starting in a minimum. And it's a cosine wave in which I have a negative. Now, I'm not going to use sine because it makes no sense to use sine. I'm going to use a cosine wave because it looks like a cosine wave. And in fact, it looks like my midline, my d value, has moved to 40. We also know that the period is 4, which is also equal to 2 pi divided by omega. So we know our omega is pi over 2. We know what the amplitude is. The amplitude is 30, so A equals a negative 30 because we're starting in a minimum instead of a maximum. And I'm not going to phase shift this. So a good choice for the function in terms of time would be negative 30, the cosine. I have my omega, which is pi over 2, multiplied by t. I don't have any phase shift. I'm choosing to use a cosine wave instead of a sine wave because sinusoidal means I can use sine or cosine. And then I know that my midline has moved up to 40. So here is a perfectly reasonable answer for that. Could I have used sine? Yes, this is what it looked like if I used sine. So f of t is equal to. My sine wave would start right here and it would end right here. So their platform, obviously, they'd be getting on this at a platform that is 40 feet up. So if that's okay too, and if I choose to use a sine wave, I still have an amplitude of 30, but it's positive because I'm going to start at the midline and then go up, and it'll be the cosine, sine, because I chose to do sine. It's not wrong to use sine as long as, of course, we've talked about this before, if this hits grid marks, I can use sine, right? I'm always looking for grid marks for sine or cosine. So I'm using sine, and that's okay. And I have my omega, which is still going to be pi over 2, except for now I have to deal with the phase shift. I'm phase shifting right 1, so it'll be a -1, and then plus 40. Now, this is also a perfectly legitimate one to use to describe the behavior. The assumption has to be for this one, though, is that for t, or these should be a t, excuse me, that should be a t. For t to be 0, right, if t is equal to 0, then the assumption is you're going to start right here, which it makes more sense to use the cosine wave versus the sine wave. The sine wave is not wrong. This is easier to use as the cosine wave just because of the way it's shaped. Now here's what we can write in sinusoidal waves. I like to, of course, if you've seen any of my videos or if you're in class, I always like to write it as this, a, and then my trig function. So I'm going to just write trig. I like to write b, or in this case would be omega, and then the x minus c plus d. And the only reason I like to do that is because I like to be able to clearly see my phase shift, and I can't really do it unless I have factored out that b. So that's the reason why I personally use the form like this, a multiplied by the trig function, and then inside the trig function, b, parentheses, x minus c, parentheses, bracket, plus d. That's all. So this is going to be a similar type of problem. The London Eye is a popular tourist attraction in London, England, and it is the largest Ferris wheel in the world. It has a diameter of 135 meters and makes one revolution every 30 minutes. Okay, so we already got some information here, and we're going counterclockwise. So here's my Ferris wheel, and I'm going to be going in this direction. We know that its period is 30 minutes, which means its omega must be 2 pi divided by 30. Or in other words, I have pi over 15. So boom, got the omega. It is constructed so the lowest part of the eye reaches the ground. So that tells me right here I'm at ground level. So unlike my previous example where I must have got it on the Ferris wheel at a platform, that if I were to draw this graph, I'd be starting right here. My maximum would be at the diameter, which is 135, and then I'd be back down here, assuming I'm going to get on the platform at 0 time and it's going to come down and look like that. So I find my midline because that will be my D. This is going to be equal to 135 divided by 2 because that I have the diameter. That means I must want the radius. And I get that to be 67.5. Again, I'm going to use cosine because this is a cosine with a negative coefficient. This distance is my amplitude. So I'm going to use cosine. So I'm going to have f of t is equal to negative 67.5 because that is my amplitude. The cosine of, I'm not phase shifting because I don't like to do that. I like to make this as easy as possible. So pi over 15 times t. And then I have the plus the midline change to, which is 67.5. I can use sine, but I just don't want to. Now here's one where I'm going to read this. This is a periodic function. The other one was 2, but this is more periodic. So it says a table lists the average temperatures of Lake Erie as measured in Cleveland, Ohio on the first of the month each month during the years 1971 to 2000. For example, T represents the average of the temperatures recorded in Lake Erie on March 1st for all the years between 1971 and 2000. So this is periodic because the assumption is that your temperatures, when we don't mess with, nature, it will be periodic. So the coldest temperature, if the coldest temperature is usually in February, we would expect it always to be in February. So this is a periodic. So I'm going to look to see, where do I see my lowest temperature? Well, my lowest temperature looks like it's 33, and it looks like it's in the second month. So if I were to graph these, so month 1, month 2. So in month 2, my lowest seems to be 33, and right before that was 36. So this is 33. Here's 36. And then it looks like my highest temperature is in month 8. So 2, 3, 4, 5, 6, 7, and 8. So right here would be my max. So it looks like if I were to graph this, this is kind of the graph that it's going to be taking. It's going to have some kind of shape like that. And then I go all the way out to month 12. Now, the assumption is this is periodic. So if I were to roll into the next year or the next set of averages, it would continue to make this shape. So what I'm going to do is I'm going to either choose sine or cosine. I think, again, cosine is going to be my friend. I am going to phase shift it over here. And the assumption is that this is going to take 12 months to come back to the February. So my period is going to be 12. That means my omega must be 2 pi divided by 12. So in other words, pi over 6. So I found my period. I have to find my midline. My midline is going to be the halfway between the highest temperature and the lowest temperature. So my D is going to be the highest temperature, which is 74, plus the 33 divided by 2. And that's going to give me the average temperature between these two. So 74 plus 33 divided by 2 is 53. So 53.5 is where my D is. So then I just have to figure out what my amplitude is. My amplitude, of course, is this distance traveled from the midline to a max or a min. So my amplitude is, and I'll do it at the absolute value. I'm going to have to put a negative on it in a minute. I'm just going to take that 74 and subtract off the 53.5, or I'm going to take that 53.3 or 53.5 and subtract off the 33. Either way, that'll give me my amplitude, the distance I've traveled from the midline to a max or a min, which is 20.5. Now I have everything that I need. I have my phase shift, I have my omega, I have everything. So f of t is equal to, I'm starting in a minimum, so it'll be a negative 20.5. I'm going to use the cosine. I'm going to put my omega first, so pi over 6. And my cosine wave should have started at 0 for my minimum, and it doesn't. So I have to shift it over 2, so it'll be x minus 2. And then we know that my phase shift is 53.5. And there it is, and I can put that in my graphing utility function or any kind of graphing calculator or Desmos or any of those, and to confirm that if I were to plot these dots, put it in 1, 36, 2, and 33, and then graph this thing, I'm going to get the exact, well, it's not going to be exact, it's going to be close. And I did that, and this is the graph. Let me just move this off to one side. Let me show you the graph that I got. Here's the graph, plotting those points and then plotting my function. Now, you can see that my function does not hit all of those points. And in fact, I messed around with my graph a little bit, and I discovered if I would have let my phi be 2.5, then it actually got closer to those points. It actually was more like that, which would kind of make sense if you were thinking about the averages and then you want to go average the month. So it'd be 2.5 instead of 2. So if you use phi being a 2.5, then you just get a little bit better of a graph. But anyways, that's how it looks. Now let's talk about harmonic motion functions. So suppose we have a string, suppose we have a spring, not a string. Reminds me of that joke, there's a spring that goes into, no. Anyways, so it's a spring. Suppose we have a spring and it has a natural length and we put a weight on it and we do nothing but allow the weight to sit on in that spring. Then this is at equilibrium. It's not moving. It's not doing anything like that. And we say this is at the equilibrium position. If we push it, if we compress it here, if we compress, then we actually say it's above the equilibrium position, and we say my x of t is less than 0. If we pull it down, we see my x of t is greater than 0, and we are below the equilibrium position. So that rest means we're right here at equilibrium, and then when I compress, it's negative, and when I stretch, it's positive. So suppose we have a spring which weighs 10 pounds, is suspended from a ceiling which stretches 2 feet to its equilibrium position when it's attached. Okay, so here's my ceiling and here's my spring, and I have equilibrium. Now, the equilibrium position from here to here is 2 feet. And we're at equilibrium. Find the spring constant K in pounds per foot and the mass of the object in slugs. So a couple of things that we know is that the force for a spring is equal to the spring constant times that distance. So we have a force of 10 pounds is equal to the K. And then the distance is 2 feet. So my spring constant solving for K is going to be 5 pounds per foot, because 2 was in feet and the force was in 10 pounds. Now that gives us our spring constant. The other thing that it's asking for is the mass. Now we know the weight is equal to the mass multiplied by the gravity. The weight is also the force. This is equal to 10. The mass is what I am searching for. The gravity is 32 feet per second squared. And this is also in feet here. Pounds. It's in 10 pounds. Okay, so what we're going to do is solve for m. When we solve for m, we end up with 10 over 32. And I end up with pounds times seconds squared divided by feet. And this unit, when I have it in this form, which is pounds per second squared feet, this unit is equal to a slug. Isn't that lovely? So my mass is, I'm going to reduce this to 5 over 16 slugs. Delicious. Okay. Find the equation of motion of the object when it's released 1 foot below the equilibrium. When is the first time the object passes through the equilibrium position, and what direction is it heading? So to answer this, I need a couple of more equations. One of the equations we have is omega is equal to the square root of this. This is for a spring. So this is undampened harmonic motion for a spring. It's equal to, the omega is equal to K divided by M. So we have the spring constant. We found that to be 5, and we found the M to be 5 over 16. So we end up with an omega of 4. So here's a formula that is important. Another formula that's important is my A. My A can be found with the square root of x naught, my starting position, plus my v naught, that would be the velocity if I have that, divided by omega, the quantity squared. So here's another equation that is useful. So we know that my A must be the square root. Well, I am starting, I'm pulling it down 1 foot below equilibrium, and this should be squared. Sorry, this should be squared. And so I have 1, the quantity squared, plus. Now, my V naught, I am not forcing it up, so I'm not giving it any kind of velocity. So my initial velocity is 0 divided by 4, the quantity squared, and so my a just happens to be 1. Now I can go ahead and do my equation, and then I can actually answer the question. Now, I'm going to use cosine because, let me just erase this. I'm going to use cosine because remember, if I am pulling down, a pulling down means I'm actually starting in the positive, and I'm going to have a positive 1. So I'm going to start in a positive, I'm going to go to equilibrium, I'm going to come back up, and then that will be where I end. So I know that my omega happens to be 4. I'm going to use cosine, so I have f of t is equal to the cosine, my a was 1, of 4t. We would like to know at what time does it pass equilibrium position. So the first time it passes is right there. Now in a regular cosine, that would happen when we are at 0. So in other words, this is the cosine of 4t is equal to 0. That's when this angle 4t would be pi over 2 if I were solving this as an equation, which means t must be pi divided by 8. So the time in which I have the first point of equilibrium is pi over 8, or approximately 0.39 seconds. So that's the time at which I am hitting equilibrium for the first time. Now the other time that I'm hitting equilibrium, if I was inclined, would be at this point. So I do this again, 4t is equal to 3 pi divided by 2, and I would end up with t is equal to 3 pi divided by 8, and whatever that is, seconds. So those are the two times that it happens. Find the equation of motion of the object when it's released 6 inches above the equilibrium position with a downward velocity of 2 feet per second. We want us to find the object passes through equilibrium position on the third time. Now, this is going to be different because I have this downward velocity. That means this is not going to be 0. Because that's not going to be 0, my amplitude is not going to just be 1 like it was before, because I have a velocity that has to be a part of the conversation. And that's beyond the scope of this class at this point. So we're not going to answer part C at this point. We are, however, going to move on and look at the fact that when you are pulling on a spring, again, the spring, not string. When you're pulling on a spring, or if you have a pendulum, that spring is not going to continue to oscillate forever. It's going to eventually start to, when you're pulling a spring, it may start like this, but eventually it's going to start to dampen down. Just like when you do a pendulum, it also starts to slow its wave down. We call that dampened harmonic motion. Now note, we're going to use sine when the motion starts at equilibrium, and we're going to use cosine if the motion starts in a compression or a stretch. So let's go through this example. The natural length of a spring measures 12 inches. The spring is compressed by 4 inches and then released. So we know all right out of the gate that we're going to be using a compression, which means we're going to start in compression, which means we're going to be using the cosine. So we know that we're going to be using cosine. We are compressing by 4 inches, so we know that the A equals -4. We have to figure out what e raised to the negative ct is. We know that it's going to decrease by 25% each time, so we know that this is the part that does the dampening. And we know that 1 minus that 25% as a decimal raised to the t has to be equal to e raised to the ct. So in other words, if I have the fact that I have the t's, they're both t's, that I really have 0.75 raised to the t is equal to e raised to the t. Now if I take the tth root of both sides, so I'm going to take the tth root, the nth root, the tth root. Sounds terrible, doesn't it? Anyways, we get 0.75 is equal to e raised to the c. So now I'm just really chasing c. So this goes back to our pre-calculus one. I'm going to take the natural log of both sides. So the natural log of 0.75 is equal to c. And I'm going to get my calculator out. And I've got c now. So I'm going to take the natural log of 0.75. And we end up with c being a negative 0.28768. So we'll go with 77. Okay. So now we have our c, we have the a, and remember our equation f of t is equal to, we found the a to be a negative 4, so we're going to go ahead and put a negative 4 in there. We also have e raised to the c, so this is going to be negative 0.2877 times t. So we found that part of it. Now, I'm going to go ahead and erase this because I need some space. We know that the spring measures a length of 12. So that's where our baseline is moving to. And then it's going to go up and down from 12. So if I were to graph this sine or cosine wave, that I know that I would be in compression of 4 inches. So down 4 inches, 12 minus 4. And then I would have had the 12 here. And so we know that it would have started to do this, and then it's going to start, and eventually it's going to go to 12, because that's where my midline is. So here's my midline. Okay, so now I just have to figure out what I'm going to use for omega. And because it oscillates once every 2 seconds, we know what our period is going to be. It's going to be 2 is equal to 2 pi divided by omega. So we know that omega must equal pi. So we have the cosine of pi times t and plus the 12. And so here's our equation for dampen motion for this spring. And that's it for this section.